Hi students, very good morning to all. Welcome back to the physics video session. So today's session we are going to discuss about the moving charges and magnetism. Chapter 4. Already we finished 3 chapters, that is 2 units, electrostatics and current electricity. So now move to chapter 4. So already we have studied about magnetism and magnetic effect of current in 10th standard also. So in 12th standard we are going to briefly discuss on magnetic forces and fields caused by the moving charges and the forces exerted on the currents and charges. So let's move to chapter 4, magnetism. So in this session we are going to discuss on the various topics, that is magnetic effect of current, Weierstrass experiment, Ampere's swimming rule, Maxwell's cork screw rule, right hand thumb rule, Biot-Savart law. These and all the simply the rules given by the various scientists, and those are very interesting topics. So magnetic field due to the current carrying conductor, and we are going to derive, these are the derivation questions. Magnetic field due to the current carrying circular loop. So this and all we are going to discuss briefly in this session. In our childhood, we all might have experienced iron nails getting attracted to a magnet. We know. We have also heard current carrying copper wire wound around an iron bar acting as a magnet in a science project. This is also we know. So that time all that seemed as a magical one, although it is all science behind it. Now we know it is due to the magnetism. So everything due to the scientific concept behind them. So magnetism is simply the phenomenon due to which moving charges are simply magnets. So we know moving charges will create the magnetic force and magnetic field, or simply we are using the bar magnets, different kinds of magnets that we are using. So those all are due to the phenomenon magnetism. They attract the ferromagnetic objects like iron, nickel, cobalt, and also repel diamagnetic objects. In olden days, that is before 200 years ago, the electricity and magnetism are considered as a different phenomena, and they are independent to each other, not related to each other. But nowadays we found that electricity and magnetism are interrelated. They are interconnected. One causes another. Simply the electricity will produce the magnetic field. Moving charges will produce magnetic field. At the same time, the changes in the magnetic field create the electricity. So these and all we know. So in 1820, connection between electricity and magnetism is given by the Christian Weierstrass. He found that the current carrying wire will produce the magnetic effects. So he connected electricity to the magnetic field. So later Maxwell, James Clerk Maxwell, unified the electricity and magnetism concept as a single one called electromagnetism. So we will discuss the electromagnetism in the upcoming chapters briefly. So first thing is magnetic effect of current. Students, already you know that is if you bring a magnetic needle, that is compass needle, close towards the current carrying wire, if you current carrying wire you consider, so just you take a magnetic needle and move towards the very close to the magnetic current carrying conductor, so the magnetic needle will be deflected. You may observe. So this is due to the magnetic field caused by the current, that is moving charges. Current means nothing but flow of charges. So here positive and negative charges may be flow. So due to the moving charges, magnetic field will be created. So that field will deflect the magnetic needle of the compass. So this was proved by the Weierstrass by his experiment, simply taking a current carrying wire, so connected with a battery, and so it is under the current carrying wire a magnetic needle is placed. So it shows the south to north portion. So current is passed through the south to north direction. When current passing through, without no current pass, so there is no deflection. If current passing through the direction towards the south to north, so the deflection will be arised like this. So the compass needle deflected some from the normal position, that is deflected left side. So this is towards the west direction. So same time, if you reverse the current, if you pass the current in the opposite direction, from north to south, so the same needle will be deflected on the right side, that is towards the east. So like this. So these are the observations made by the Oersted and concluded, and simply we can again do it by experiment. Just you place a magnetic needle so under the current carrying wire like this. By holding some stand, the magnetic compass was held under the current carrying wire, and now no current is passing through the wire, there is no deflection, it shows the direction south to north. This is the first case. So in this case, if the current is passing through this direction, that is south to north direction, current is passing through south to north direction. So now the magnetic needle will be deflected on the left side, that is west direction. So this is the first case. In the second case, the current is reversed, the current is passing through opposite direction. In the first case, current is passing in this direction. In the second case, current is passing in this direction, that is north to south, that is current direction is this. So now the magnetic needle will be deflected on the right side, that is east direction. So similar way we can do two more cases. In the third case, now here the magnetic compass needle is taken above the wire, the same current is passing through south to north direction, the magnetic needle deflected on the now right side, that is east direction. The same thing, that is magnetic needle was above the current carrying conductor and current is passing through the direction from north to south. Now the deflection will be west direction. So these four cases should be remembered. So students, we can conclude that the charges moving through the conductor or the current passing through the conductor will produce the magnetic field around it. So this direction of magnetic field can be arrived by the saying the three laws. That is, first one is the Ampere swimming rule and Maxwell's corkscrew rule, and also right hand thumb rule. So these three rules are used to determine the direction of the magnetic field. First one is the Ampere swimming rule, or it is called a snow rule. So here just you imagine a man swimming in the direction of current from the south to north direction, so and also facing a magnetic needle kept under him, so such that current flows from through his feet, that is current passing through the south to north direction. So then the north pole of the needle will deflect towards the his left hand, that is towards the west, because he is facing the south to north direction. So the deflection will be left hand, means west direction. So this is called Ampere swimming rule. Simply a man swimming along the direction of south to north, on the way current is passing, and he is facing the magnetic needle kept under him. So simply if current passing through the south to north, then the deflection will be in the left direction, that is west direction. Suppose the direction of the current changes, so also the deflection will be changed to the east direction. So this is Ampere swimming rule. Here snow means there is current passing through south to north over the magnetic needle, and deflection will be west direction. So that is called snow, south to north over west direction. And second law is given by Maxwell, so it is called corkscrew rule, or simply right hand screw rule. So the statement is, if the forward motion of imaginary right handed screw is in the direction of the current, so simply the forward motion is shows the direction of the current, then the direction of rotation of the screw gives the direction of the magnetic field. So this is called right hand screw rule. Simply the screw, if you move the screw in forward direction, we should give the pressure, and it will be rotated on the clockwise direction. If you rotate the screw in clockwise direction, so then only it will move forward. So if you rotate the anti-clockwise direction, it will be loosed and it will be backward direction. So this is the normal phenomena of screw. So we can compare this screw with the magnetic effects of current. So the current passing through the forward direction of the screw, then the magnetic field produced by the current is given by the clockwise direction. So this is called screw rule. The third one is the right hand thumb rule, or simply called curl rule. Curl means rotational rule. So it denotes the right hand thumb. Just you take the right hand thumb. So statement is, if a current carrying conductor is imagined to be held, this is the current carrying conductor imagined to be held on the right hand, such that is thumb points in the direction of current. The current is passing through the conductor like this direction. So the thumb shows its direction. So then the tips of the fingers, so these other fingers encircling the conductor will give the direction of the magnetic lines of force. So this is called right hand thumb rule. Simply all three laws give the direction of the magnetic field. So this same case, if you take this direction, now current carrying this direction, so the direction of the magnetic field will be, so this anti-clockwise direction. Suppose current flow in this direction, so this is given by clockwise direction. So all three law has given the same statement, that is direction of the direction of the current, direction of the magnetic field due to the current carrying conductor. So we can use any rule to find out the direction of magnetic field, that's all. Next, Biot-Savart's law. This law is used to find out the magnetic field at a point due to the current carrying conductor. So current passing through the conductor is I, and a small element of length dl is considered. So due to this small element, we are going to find the magnetic field at the point P. So the distance of point from the dl is r. So it is taken as position vector r vector, and theta is the angle between the position vector r and the area, that is current element dl, that is theta. So now the magnetic field, usually magnetic field is denoted by B. Here due to the small element dl, so dB is taken. So the magnetic field dB due to the small element at the point P is directly proportional to the, is given by this law, directly proportional to the current. First one is current, and also directly proportional to the length of the current element. Third one is directly proportional to the sin theta, where theta is the angle between the P and dl. And finally, the magnetic field is inversely proportional to the square of the distance between the point and element, current element. So that is 1 by r squared. So combinedly we can write, that is dB is 4 parameters are there. First one is directly proportional to I, and directly proportional to dl, and directly proportional to sin theta. Finally inversely proportional to 1 by r squared. So we can combinedly write dB is proportional to I dl sin theta by r squared. In order to remove this proportionality constant alpha proportionality, so we include the constant, that is dB equal to, that constant is mu naught by 4 pi. To remove proportionality, we include mu naught by 4 pi into I dl sin theta by r squared. So this is the magnetic field due to the current element, the current passing through the wire, where mu naught is called the permeability of the air or free space or vacuum. So the permeability means simply the ability of allowing the magnetic field in that medium, that's all. So next we see the same formula in the vector form, Biot-Savart law in vector form. Usually dB equal to mu naught by 4 by I dl sin theta by r squared. So magnetic field is a vector quantity. So dB vector is equal to taken as mu naught I by 4 by dl vector into r cap, where r cap is the unit vector along the direction of r vector, position vector of the point. So we can write the vector form dl vector into r cap. So we unit vector can be written as r cap equal to r vector divided by magnitude, that is r. So substitute the r cap. So replacing r vector by r, we can write dB vector equal to, can write dB equal to mu naught by 4 pi I into dl vector into r vector by r cube. So now substitute that is r vector equal to r into r cap. So r get cancelled, only we can write r cap by r squared. So this is the vector form. Here dl vector I dl vector cross r vector, which gives the dl sin theta, whose value r cap value is 1. So finally gives I dl sin theta. So this is the vector form of the Biot-Savart law. So both are vector forms. Here mu naught equal to 4 pi 10 to the power minus 7 Tesla meter ampere power minus 1. Tesla is called the unit of magnetic field, or Weber meter power minus 1 ampere power minus 1, because Tesla equal to Weber per meter squared. So substitute the Weber per meter squared instead of T, we obtain this formula. Also Tesla is the SI unit of the magnetic field. So like the SI unit of charge is coulomb, it's a very big rather the larger, it is macroscopic unit. Similar way for Tesla, T is the Tesla, which is the SI unit of the magnetic field. So usually we are using the Gauss. So 1 Tesla equal to 10 to the power 10 to the power plus 4 Gauss. So 1 Gauss equal to 10 to the power minus 4 Tesla. So this is the unit of magnetic field. Tesla is the SI unit. Other unit will be Weber per meter squared or Gauss. So here the value of mu naught is 4 pi into 10 to the power minus 7. So here direction of the magnetic field dB is same as that of the direction of dl vector into r vector, which gives the vector product, to gives the vector. So the direction will be the magnetic field direction, and it is vector product of current and length of the small element having the direction of the flow of current. Here the point is given like that, it is emerging at p dash, that is it is given by dot. Emerging means dot, it's a magnetic field coming outwards, so it is denoted by the dot. At the point P, the plane of the diagram, so it entering inside the plane of the diagram, so it is marked by cross. So simply by seeing this diagram we can understand. So here the magnetic field is entering inside, that is entering inside the plane of paper. Here outside, it away from inside the plane, it comes out, so emerging out at the p dash, so entering inside at p. So this is the direction of the magnetic field. So magnitude is given by the vector form and also the normal form. dB equal to mu naught by 4 pi I dl sin theta by r squared, or mu naught by 4 pi I dl vector cross r vector by r cube. So this is called Biot-Savart law, which is used to find out the magnetic field at any point due to the current carrying conductor. So thank you students.